Good evening, everyone. So today in this session, we'll be starting with the chapter Semiconductor Devices, right? So before discussing anything about the semiconductor devices, we'll be doing a qualitative discussion over the classification of the solids, right? Different types of solids we have on the basis of their conductivities, right? So basically, we have when we broadly classify the solids, we can classify the solids on the basis of their conductivity into three categories, right? The first category is the conductors, and another is the insulators, and the third category is the semiconductors, right? But this classification is done uh, based on the conductivity of all the three materials of solids, right? So we know conductors are the materials, right? Conductors are the materials of high conductivity, right? They are the materials of the high conductivity. We'll later on discuss conductivity of these materials in detail, right? But conductors are materials of high conductivity, right? They are materials of high conductivity. So their conductivity is actually high, right? Or we can say they are materials of low resistivity and high conductivity, right? Now, for the insulators, the conductivity is almost zero, right? Very less conductivity or zero, right? Or we can say the conductivity of insulators is equal to zero, right? So they do not conduct any current, they do not conduct any current at all. Whereas the conductors are the we can say the materials of high conductivity, right? They conduct the current electricity very easily, right? Now, talking about the semiconductors, the conductivity of the semiconductors lies between that of insulators and conductors, right? So their conductivity is between conductors and semiconductors, right? Between conductors and insulators, right? That's the conductivity of semiconductors. Or we can say their conductivity is very less than the conductivity of conductors, but high conductivity than the conductivity of insulators. So insulators have the zero conductivity, right? Or we can say semiconductors are the conductors of intermediate conductivity, right? Now talking about the resistivity, so conductors are high conductivity of their conductivity is high, or we can say their resistivity is less, right? So their resistivity is less. We can say that conductors are of less resistivity, right? Less resistivity, right? And they are having insulators are having high resistivity, right? And semiconductors have intermediate resistivity, right? Intermediate resistivity, right? Is that of the semiconductors. Now let's talk about the effect of temperature on all the three materials, right? We know that insulators do not have any free electrons for the conduction, right? For conductors, the electrons are freely available for the conduction, and there is a fair availability of electrons in case of semiconductors for the conduction of current electricity, right? Now, talking about their effect on the conductors, insulators, and semiconductors because of the increase or decrease in the temperature, right? Because of the increase or decrease in the temperature. We know that insulators, there are no free electrons present, right, at all. Or we can say the electrons are very closely bound to the nucleus of an atom, right? They are not freely available, right, for the conduction, right? So when we increase the temperature of insulators, there is no effect on the insulators with the temperature, right? Their conductivity still remains the same, right? But when we talk about the conductivity of conductors, right, on increasing the temperature, right? So when we increase the temperature, the conductivity of conductors actually decreases, right? So on increasing temperature, right, is the temperature or increasing the temperature of conductors, right? Their conductivity, that sigma, right, that's the conductivity that decreases, right? That decreases, or we can say their resistance increases, right? So the resistance of conductors increases on increasing their temperature, right? So there is almost no effect in case of insulators, right, on increasing the temperature, right? But in case of semiconductors, the resistivity or the resistance of semiconductors decreases on decreasing the temperature, right? On increasing the temperature, resistance decreases, when the temperature is increased, right? When the temperature is increased, or we can say their conductivity increases, right? Conductivity increase in case of semiconductors, right? So it means that if we increase the temperature of semiconductors, their conductivity increases, or we can say they become a good conductors of the electricity, right? Now there is a term what we call as a temperature coefficient of resistance, right? That's the alpha, right? That's the alpha. We know that this alpha is actually positive for conductors, because the change in the resistance is actually a positive in case of conductors. When we increase the temperature, the resistance increases, right? This alpha is actually defined as is the relative change in resistance per degree rise in temperature, right? Per degree rise in temperature. So it's the relative change in resistance per degree rise in temperature, right? And this is positive, right? Means it is greater than zero for conductors, and for semiconductors the resistance decreases on increasing the temperature. It means the change in resistance will be a negative here, or we can say the alpha will be negative for semiconductors, right? Or we can say it will be less than zero. That's equal to delta R upon R, right? Delta T. So this is what we call as alpha. This is the relative change in resistance per degree rise in temperature, right? So this is how we can differentiate between the three materials of the three materials of the solids, right? One is conductors, insulators, and semiconductors based upon their conductivity, right? So the conclusion is that conductors are of high conductivity, insulators are of zero conductivity, they do not conduct at all, and semiconductors, the conductivity of semiconductors lies between that of insulators and conductors, right? And the temperature coefficient of conductors is positive, while the temperature coefficient of semiconductors is negative, because the resistance of semiconductors decrease, right, upon increasing the temperature, while the resistance of conductors increase upon increasing the temperature, right? Now, now let's discuss how actually the conductivity takes place, right? In case of solids, we know that if we have an isolated atom, right? If we have an isolated atom, right? So let's suppose we have carbon atom, right? Carbon has 6 electrons, right? 2 electrons are in its first orbit, and the rest 4 electrons are in its second orbit, right? So this is the electronic configuration of carbon, or we can say this is the electronic configuration of isolated atom, right? Similarly, if we have a silicon, right? Silicon has the atomic number of 14, right? It means that the neutral silicon atom contains 14 electrons, right, in its orbit, right? So if we draw the electronic configuration for the silicon, right? So the electronic configuration of silicon will be equal to, it will be 1s2, right? 2s2, right? And we'll be having the 2p6 configuration, right? That will be the 2p6, right? So it will be 2p6 and 6 and 4, and then we'll be left with 1s2, 2s2, 2p6, right? And then it will have 3s2, right? 3s2. Then we have 2p. The configuration will be there will be 14 electrons for the silicon, right? 2 electrons in the first orbit, right? And 8 electrons in the second orbit. Will be left with 6 electrons that will be in the third orbit, right? So this configuration will be 1s2, right? This will be, and then we had 3p4, right? We will have 3p4. It means that the valence, the outermost shell of this silicon will have 6 electrons, right? It will have 6 electrons, right? These 2 electrons will go into 1s2 orbital, right? These 8 electrons will go into 2s2 orbital, and we will have 6 electrons in 2p, right? That's 6 electrons in 2p orbital, right? Of uh, n equal to 2 quantum number, right? Similarly, we have 6 electrons that will go into 3s2, right? 3s2 and 3p4, right? So this will be the uh, electronic configuration for the silicon atom, isolated silicon atom, right? Now we can see here 3s orbital is a fully filled orbital, and right? It's a stable orbital, right? Now talking about 3p4, it's a partially filled orbital, right? It means that this orbital will take part in the bonding, right, in case of solids, right? Now talking about the isolated atom, right? This is the isolated silicon atom, and all these electrons are in orbits, right, according to the Bohr model, right? If we talk about the isolated silicon atom, there are 2 electrons in the first orbit, there are 8 electrons in the second orbit, and there are 6 electrons in the third orbit, right? For n equal to 1, we have 2, and for n equal to 2, we have 8. For n equal to 3, we have 6 electrons, right? Now, all these electrons have this fixed energy, right? As according to the Bose model, these electrons will have some energy, right? Some energy in their orbits, right? They must be revolving around the nucleus with some fixed energy, right? With some fixed energy, right? So for these electrons, the energy is actually a fixed energy, right? And for every isolated atom, right? But the question is that when we draw the energy level diagram of isolated atom, right, we obtain different energy levels corresponding to the different electrons in different orbits, right? Now the question is that what happens to these atoms when these atoms are part of a crystal, right? Part of a crystal, right? We know that a single piece of crystal contains infinite number of atoms, right? It contains infinite number of atoms, right? And all these atoms are arranged in some fashion in a crystal, right? In some fashion in a crystal. That's what we call as the arrangement of the atoms in a crystal, right? So, what happens to those atoms which are in a crystal? And because when the atom is in a crystal, there are interactions between the atoms, right? There are interactions between the atoms. There is a nuclear interaction, or we can say the positive charge of one nucleus interacts with the positive charge of another nucleus. Similarly, there is electronic interaction, or we can say the energy that electron the energy of the electron in an isolated atom now cannot be the same as energy in a crystal, because there are now different interactions happening between the atoms in a crystal, right? Now what happens is that now this energy levels actually get separated into number of energies, right? And we get a band of energy levels, right? We get a band of energy levels, and those bands we call as energy bands in solids. So in case of crystals, we do not have a discrete energy levels, but we have the band of energy levels because of the different interactions happening between the atoms in a crystal, right? So you can see here, if we consider a single crystal of silicon having n number of atoms, right? And each position of atom in a crystal, what we call as lattice site, right? That's what we call as lattice site, right? And each lattice site actually interacts with number of atoms, number of neighboring atoms. So because of that interaction, the energy level of each electron actually gets split into number of levels, right? And we get a band of energies, right? That's what we call as energy bands. Now you can see this is the diagram. This is how the arrangement of atoms are in a crystal, and each position of the atom in a crystal is what we call as a lattice site, right? So it's because of the interaction between the atoms, or let's suppose this is a silicon atom. The silicon atom in a crystal will interact with all the neighboring atoms, which will lead to the change in the energy of electrons, and eventually it will lead to the formation of energy bands, right? Now talking about the inertials, right? Talking about the inertial, the interaction of the inner electrons, it is not much appreciable, right, in case of crystals, right? But it's very much appreciable in case of the outermost electrons that we call as valence electrons, right? So the discrete energy levels now, because of the interaction, get splitted out, right, to form a band of energies, right? That's what we call as energy bands. Now we have two types of energy bands here, right? Two types of energy bands are formed. One band we call as valence band, right? Valence band, this is the band of lowest energy, or the stable energy band, right? This is lower energy band which contains the valence electron, right? So band of energy is formed by the valence electrons are of two types. One is the valence band, another is the conduction band, right? So valence band is a energy band of least energy or lower energy, right? This can be partially or completely filled with electrons, but this valence band is never empty, right? Valence band can never be empty. It can be a fully filled band, or it can be a partially filled band, but it can never be an empty band, right? And the electrons present in the valence band, right, are not available for the conduction, right? They do not take part in any conduction, right? Or we can say the electrons present in the valence band are not available for the conduction, or they do not take part in conduction of current, right? Now, second band formed because of the interaction of the valence electron, that's what we call as the conduction band, right? This is a higher energy band, right? The electrons present in this conduction band, we call them as conducting electrons or conduction electrons, right? This band can be empty or partially filled, right? And electrons of this band actually take part in the conduction of electricity or the conduction of current, right? So this is how the electricity is conducted uh, in case of solids, right? So there are two bands. One is the valence band, another is the conduction band. Electrons in the valence band do not take part in the conduction or current electricity, or we can say the electrons in the conduction band actually take part in the conduction of the current, right? Now you can see here, in this picture, we have two bands here, right? One we call as the conduction band, another we call as the valence band, and there is actually the gap between the two bands, right? In between these, in this gap, what we call as forbidden gap or forbidden energy gap, because in this gap there is no electron present, right? There cannot be any electron between these two bands. That's the valence band and conduction band. Either the electron will be in the valence band or the electron will be in the conduction band, right? So this energy which is forbidden here, we call it as forbidden energy gap for the electron, right? Forbidden energy gap for the electron. Now let's suppose that we want to excite an electron from valence band to the conduction band, right? Let's suppose the energy of this conduction band is EC and the energy of this valence band is EV, right? Now, if we want to transit this electron from conduction valence band, right, from valence band to this conduction band, right, we need to supply the energy equal to the energy gap between the conduction band and valence band to transport an electron from valence band to conduction band, and this electron now will be available for the conduction in case of solids, right? So this energy we call as energy band gap, right? Eg, delta Eg, that's equal to conduction band energy minus the valence band energy. So this is the conduction band energy, right? So the minimum energy required to shift an electron from valence band to conduction band is called as the band energy gap, right? Now, band energy gap is different for different solids. So, band energy gap will depend upon the nature of the solid. It will depend upon the interaction between the atoms in a crystal of a given solid, right? So, it is different for different crystals, right? It strongly depends upon the interatomic separation, right? Because if the separation is more, the interaction will be different. If the separation there and two atoms are very close to each other, there will be a lot of interaction between the atoms, and the energy gaps will be different, right? So the range of this valence band, or we can say the energy gap, forbidden energy gap for different solids of different materials is different depending upon the interatomic interaction between the atoms in a given crystal, right? So it also depends upon the temperature, right? It also depends upon the temperature. Now let's suppose if we increase the temperature, then what is going to happen? The energy of the electron is going to increase. The thermal energy of electron will increase. If the thermal energy of the electron increases upon increasing the temperature, right? So this electron will make a transition, right? This electron can make a transition from valence band to the conduction band, right? Or we can say the energy band gap between the conduction band and the valence band will actually decrease, right? So we can say that this energy gap will depend upon the temperature as well. Upon increasing the temperature, the band gap actually decreases, right? Now you can see how we can classify different solids based upon the energy band theory, right? So we have conductors, semiconductors, insulators. So conductor here, for example, we have copper, iron, aluminum, right? These are the metals. Sodium is also a metal, right? It's a conductor, right? Then we have semiconductors like silicon, germanium, right? We have what we call as inorganic semiconductors. That's gallium arsenide, right? And then we have the insulators like diamond, wood, extra, right? You can see here, in case of conductors, actually the conduction band actually overlaps with the there's a complete overlap between the conduction band and valence band in case of conductors, or we can say the band energy gap between the valence band and the conduction band in case of conductors is almost equal to zero, or we can see all the electrons in case of conductors are available, right? All the free electrons are available for the conduction, right? So that's the reason the conductors are the best conductors of electricity, and they are having the high conductivity because the conduction band and the valence band overlap in case of conductors. Now, talking about the semiconductors, the energy gap, right? The energy gap between the conduction band and valence band, it's almost approximately equal to the lies in the range of 1 electron volts, right? It lies within the range of this 1 electron volt, right? So this is the energy gap between the two bands, right? Conduction band and the valence band in case of semiconductors. So there is a small amount of energy required for the electron to make a transition from the valence band, right? From the valence band to the conduction band, so that it will be available for the conduction in case of semiconductors, right? But in case of insulators, there's a huge gap between the conduction band, right? There's a huge gap between the conduction band, and this gap is actually greater than the 3 electron volts, right? It's actually greater than the 3 electron volts, or you can say there's a huge gap between the conduction band and valence band in case of insulators. That's the reason we can say that the insulators are actually the bad conductors of current electricity, right? They are the bad conductors of uh, electricity, right? Now talking about different types of the semiconductors based upon the purity of the semiconductors, we have two types of semiconductors broadly speaking. One type of semiconductor we call as intrinsic semiconductor, another we call as extrinsic semiconductor. Actually, the uh, intrinsic semiconductors are the pure semiconductors, right? They are the pure semiconductors. There is no impurity uh, in the configuration or in the composition of these materials, right? They are the semiconductors of the purest form, right? We call them as intrinsic semiconductors, right? So intrinsic semiconductors behave like a perfect insulator, right? Because in case of intrinsic semiconductors, they have almost negligible number of free electrons, right? Free electrons. They are free from any type of impurity, right? The covalent bonds formed between the atoms of these semiconductors are actually complete, right? So that there are no free electrons, right? Now, the free electrons can only be available, right? Can be only be made available in case of intrinsic semiconductors when we increase the temperature of a semiconductor, right? And because of the thermal agitation, or we can say because of the thermal motion of the electrons upon increasing the temperature, there maybe the bond breaking may take place between the atoms, and because of the breaking of the bonds, the electrons may become free. Some electrons may become free, and they will be available for the conduction, or we can say the electrons in the valence band may shift to the conduction band and will be available for the conduction, right? So that's only possible when there is a slight increase in temperature, or we can say at room temperature there is a slight conductivity, but it is almost negligible, and that conductivity is only because of the breaking of the covalent bonds in case of intrinsic semiconductor, right? In general, we can say that valence bands are completely filled, conduction bands are completely empty, right? Valence bands are completely filled, and the conduction bands are completely empty in case of intrinsic semiconductors. That's why we can say at absolute zero, intrinsic semiconductors will actually behave as a perfect insulators, right? Because at absolute zero temperature, there will be no thermal motion, there will be no bond breaking, there will be no availability of electrons in the conduction band, right? So there will be no transition of electrons from the valence band to the conduction band, or we can say the conductivity of intrinsic semiconductors at lower temperature or absolute zero is actually equal to zero, right? They behave like a perfect insulators. So these semiconductors we call as intrinsic semiconductors. These are the semiconductors of purest form, right? There is no impurity added to these semiconductors, right? You can see here, this is the diagram of uh, energy diagram of this kind of semiconductors, right? There is a conduction band, right? This is the EC, or the conduction band, and we have this what we call as valence band, that's EV, right? And you can see there's no electron present in the conduction band, right? So it is empty actually, right? We can see that it's actually empty. Conduction band of intrinsic semiconductors are empty, right? And the valence bands are completely filled, right? They're completely filled. Valence band of intrinsic semiconductors are completely filled, right? While the conduction bands are empty, right? They are empty, right? and at absolute zero they behave like a perfect insulator, right? So this is the this was the you can see here let's suppose if we increase the temperature, let's suppose we're keeping the temperature around 300 Kelvin, 350 Kelvin, right? We have slightly increased the temperature, right, of around 50 degrees centigrades, right? So this 50 degrees centigrade, it will be around a temperature of 325 Kelvin, right? So it we can say that even at room temperature, right, you can see the valency, or we can say the number of valence electrons in case of silicon, they are 6, right? The electronic configuration of the outermost shell of silicon is 3s2 and 3p4, right? There are 4 electrons in the p orbital and there is 2 electrons in the s orbital, right? So to complete its octet, right, silicon will tend to will try to make a bond, right, with respect to with other silicon atoms in a same crystal, right, to complete its octet. So the bond formation will be a covalent bond, right? So it will be a covalent bond. Now what happens is that when we increase the temperature, right, when we increase the temperature, let's suppose we increase the temperature, and upon increasing the temperature there will be thermal agitation, and because of that thermal agitation the electron will gain some energy, and this electron will be thermally generated, or it will be removed from this site, right? It will be removed from this site, and when this electron will be removed from this site, and this electron will jump these few electrons. Let's suppose this electron also gets removed, right? And let's suppose this electron also gets removed. All these electrons move to the conduction band, right? They move to the conduction band. Now they are available for the conduction. You can see here, upon increasing the temperature, there is a slight population of the electron in conduction band, right? There is a slight population of electrons in conduction band, you can see, but this population is actually a very small population of electrons in conduction band, right? And this population is because the bonds break because of the increase in the temperature, because of the thermal agitation between the atoms, right? Or we can vibration between the atoms. The electron gain the energy, then the electron jump from the valence band to the conduction band, and there is a small amount of conduction in case of now intrinsic semiconductors upon increasing the temperature, right? Now you can see now initially this conduction band was completely empty, right? Now this conduction band is now filled with some of the electrons, right, in the conduction band, which because of those electrons the conductivity of this intrinsic conductor increases, right? Now you can see here, once the electron leaves its site within the crystal, right, it goes into the conduction band, right? It's available for the conduction, but it leaves behind a electron deficient site. It leaves behind an electron deficient site. Now this electron deficient site, or electron deficient vacancy left, right? Now this site has been left, and this site is an electron deficient site now, right? We can call this as electron deficient site, electron deficient site or vacancy, right? Now this electron deficient site or vacancy is what we call as hole, right? This is what we call as hole. So while coming out of the covalent bond, the electron leaves behind a vacancy that we call as hole, and this process of creation of electron into the conduction band and hole created at the lattice site, this is what we call as electron hole pair generation, right? So electron hole pair is actually generated, right, because of the thermal agitation or because of the increase in the temperature, right? So it actually creates the electron hole pair, right, in case of intrinsic semiconductors, right? And because of that there is a conduction. Now we know by upon increasing the temperature, the resistivity of semiconductors decrease, and upon decreasing the resistance, the conductivity of the semiconductor actually increases, or we can say the band gap between the conduction band and valence band actually decreases, right, upon increasing the temperature. Now we have actually drawn two different band gaps for two different elements, right? There is a band gap of 1.1 electron volt. This is for silicon, right? This is for silicon. The energy band gap for the silicon is 1.1 electron volt, and the energy band gap for germanium, another semiconductor, right, is equal to we can say Eg here, energy band gap for germanium is equal to 0.7 electron volt, right? And the energy band gap for the silicon here is 1.1 electron volt, right? Now, if we provide a sufficient energy for the electron in the valence band, let's suppose we provide energy equal to this band gap energy to the electron in the valence band, equal to the 1 point electron volt, then what's going to happen? This electron will jump from the valence band to the conduction band. And similarly, if we provide energy equal to minimum energy equal to zero point 0.7 electron volt in case of germanium, this electron is going to jump from the valence band to the conduction band, and now it will be available for the conduction. Let's suppose the energy, we supply the energy, light energy to this electron, right? Let's suppose the electromagnetic radiation is supplied to this electron, right? And let's suppose the energy of this electromagnetic radiation is E. If E energy is supplied, then the energy of this radiation will be Hc upon lambda, right? Hc upon lambda, right? And it will be equal to the energy band gap. That's delta Eg, right? Delta Eg. That will be equal to 1.1 electron volt, right? Or we can say the wavelength will be equal to 12400 upon 1.1, right? That will be equal to lambda in angstroms, right? Or we can say the energy supplied, the radiation of wavelength equal to this, right, will actually agitate an electron or transit electron from valence band to conduction band in case of silicon, right? In case of silicon. So this much of radiation will be actually, radiation of this wavelength will be required to make a transition from, ideally speaking, this much of wavelength will be required, right? Now talking about the electron hole pair current, right? Talking about the electron hole pair current, right? So electron and hole current. We know in conductors current is caused by only because of the motion of electrons, but in semiconductors the current is because of both the electron as well as the holes created, right? The holes created at the lead side. So electron current that is caused by electron motion, we call that as electron current, right? And the current that's caused by hole motion is called a hole current, right? So electron is a negative charge carrier, and a hole it's a positive charge carrier because it's a electron deficient site, right? Electron deficient site, it behaves like a positive charge carrier, right? So at absolute zero, we know that at absolute zero there is no thermal agitation, right? There is no thermal agitation in case of semiconductors, right? At absolute zero. So we can say that at absolute zero, the conduction of the current in case of intrinsic semiconductors is actually zero, or it behaves like a perfect insulator, right? So when the outermost orbit electron get enough energy, then they will break bond, right? And with the nucleus of atom and jump into the conduction band. The electron present in the conduction band are actually not attached to the nucleus, right? They are very far from the nucleus and they are available for the conduction, right? They are freely available to move, right? So when a bond is broken, there are two things created. One is the electron is created into the electron is making transition to the conduction band, and hole site is created. And this movement of electron and hole actually creates a current, what we call as electron and hole current, right, within the semiconductor, right? Now you can see here, if we draw the circuit diagram here, if we draw the circuit diagram here, right? Let's suppose this is the circuit diagram, or we can say if we connect this semiconductor with the battery, right? If we connect this semiconductor with a battery, right? This semiconductor is connected to the battery, right? There will be actually two types of conduction. One will be the hole conduction, another will be the electronic conduction, right? Now this is the battery, right? The electric field will be actually along this direction, right? Electric field will be actually along this direction, and the electron will move opposite to the electric field, and hole behaves like a positive charge carrier. It will move along the direction of the electric field. So this is actually the movement of hole, right? This is actually the movement of hole, and this is the movement of electron, right? Movement of electron. So the conductivity of both uh, the conductivity of both electron as well as hole will give the total conductivity of this semiconductor, right? That will be total conductivity. If that's sigma, right, that will be sigma E plus sigma H, right? And we know that conductivity is given as it's let's suppose number density of electron is Ne, right? Ne, and the number density of hole is Nh. So we can say it's a number density of electron, right? Number density of electron. Number density of electron. And similarly, Nh is number density of hole. And this will be equal to number density, right, into electronic charge multiplied by the mobility mu, right, where mu is nothing, it's the mobility, right? And mobility is defined as drift velocity per unit electric field, right? Drift velocity per unit electric field, this is nothing, this is the mobility, right? This is mobility, right? So let's suppose sigma is the total conductivity and sigma E will be Ne multiplied by the charge of electron, right? Multiplied by the mobility of electron. And similarly, will you have uh, conductivity of hole equal to uh, density of hole pairs, right? Number density of hole, right? Multiplied with the charge of electron, right? And the mobility of hole, right? Or we can write it equal to, so E will be common here. It will be Ne multiplied by E mu E, right? Plus NH multiplied by mu H, right? So this will be the total conductivity of an intrinsic semiconductor, right? If they are connected with a battery or to a circuit, right? Now, broadly speaking, we have two types of extrinsic semiconductor, right? Now, let's suppose we know that the intrinsic semiconductors are actually the bad conductors of the electricity. The conductivity is very less, right? So, because of the unavailability of the conduction electrons or the electrons in the conduction band, right? Now, in order to increase the conductivity of these intrinsic semiconductors, we actually have to add some impurity to them. Now, if we add the impurity to these semiconductors, right, uh, adding impurity to the intrinsic semiconductors, right, increases their conductivity, and such semiconductors we now call as extrinsic semiconductors, right? So, extrinsic semiconductors are formed from the intrinsic semiconductors by adding some impurities, right? And the impurities, those impurities added, we call them as dopants, or we call this process as doping, right? We call this process as doping. So doping is a process of adding some impurities to an intrinsic semiconductor in order to increase their conductivity, right? And the material or impurity added to the intrinsic semiconductor, we call that as dopant, right? And the process is called as doping, right? So doping is done to the intrinsic semiconductor to make it extrinsic semiconductor in order to increase its conductivity, right? So because at room temperature, the conductivity of intrinsic semiconductor is very low, right? So with the at the room temperature with low conductivity, no such device can be developed using these semiconductors, right? So therefore, we have to necessarily use uh, dopants or to the doping to these intrinsic semiconductors in order to increase their conductivity, right? So that we can use some important electronic devices, right? In different applications, right? In different applications. And how this doping is done? The doping is actually done in a small amounts, right? This doping is actually done in small amounts. We can say it's done in ppms, right? It's parts per million. It means that one dopant is actually added for the million parts of the pure semiconductors, right? So it's about 1 ppm or max about 2 ppms, right? Or we can say it's in ppms, right? So this is how the doping is done to the semiconductor in order to increase its conductivity, right? So the conductivity of semiconductor actually increase manifold, right? Such material we call as extrinsic semiconductors, or the semiconductors of what we call as impurity, right? Now there are two types of impure semiconductors, right? Or extrinsic semiconductor. One we call as N-type, another we call as P-type semiconductor, right? Now let's suppose we have silicon, right? In case of silicon, we know that it in its outermost orbital, right? It's in its valence orbital, it has 4 electrons, right? It has 4 electrons, or we can see in its outermost orbit it has 6 electrons, right? So it will try to make 2 covalent bonds in order to complete its octet, right? So what we do is that we add dopants to this silicon, right? Silicon or germanium, because these are both these silicon as well as germanium, right? Uh, their configuration will be uh, in their orbital, right? In their outermost orbital, there will be 4 electrons, right? In the outermost orbit or valence orbit, right? 4 electrons in both the silicon and germanium. So we can say that they need 2 more electrons to complete their configuration, right? For germanium as well as silicon, right? For germanium as well as silicon. Germanium has uh, atomic number of 37, right? 37, right? So that's how the electronic configuration is filled, right, for germanium, right? So what we do in case of silicon and germanium, we add the pentavalent impurity so that they can complete their configuration, right? They can complete their configuration, or we can say when the pentavalent impurity is added, right? Pentavalent impurity is added in case of silicon. So the pentavalent impurity can be added using the phosphorus, right? It can be added using the antimony, right? It can be using arsenic, right? So actually group 15 elements are used in case of group 14 elements to add the impurity to them, or we can say to add the pentavalent impurity to them, right? So the pentavalent impurity is actually done added using the elements of the group 15 of the periodic table, right? Where we have phosphorus, where we have arsenic, we have the antimony as well, right? So because of that, when the pentavalent impurity is added, then what we get is that we get the free electrons because of the pentavalent impurity, right? So such electrons from impurity atoms will have energy less than the energy of the electron in the conduction band, right? So it means that these free electrons, right? These electrons actually require very small amount of energies, right? These are very loosely bound electrons, right? In case of pentavalent impurity, and this electron actually requires a very small amount of energy of the order of 0.05 electron volt in case of silicon, and of the order of 0.01 electron volt in case of germanium, right? So if this less amount of energy is required for the transition of this electron upon adding the pentavalent impurity from the valence band to the conduction band, it means that it will actually we can this amount of energy will be easily available for this electron. It can actually very easily make a transition from the valence band to the conduction band and will be available for the conduction, or we can say the conductivity of this n-type semiconductor will increase many folds, right? It will increase many folds, right? And similarly for p-type semiconductors, same semiconductors are used, silicon and germanium. Now what we do is that we increase the trivalent impurities. In trivalent impurities, we have boron, we have aluminum, we have indium, we have thallium, right? Or we can say the group 13 elements are added, right? The elements of the group 13 in the periodic table, right? In the modern periodic table, the elements of the group 13, right? Starting with the boron, right? These elements are actually added to actually create or add the trivalent impurity to these intrinsic semiconductors of silicon and germanium to create p-type of semiconductor, because the vacancy of trivalent impurity may be filled with an electron from a neighboring atom, right? When that vacancy actually is filled with a neighboring electron, this creates a hole in that position, right? From where the electron actually jumps, right? So this actually creates the acceptor impurity, produce an energy level just above the valence band, right? So we can say that this type of impurity, or these type of semiconductors we call as p-type semiconductors, right? There is a trivalent impurity, right? There is a trivalent impurity added to these type of semiconductors, or we can say the acceptor level or we can say that electrons from the valence band can therefore easily move into the acceptor level by being thermally agitated, or if we increase the temperature of the semiconductor, right? So broadly speaking, now we do not go for the intrinsic semiconductors because of their low conductivity at room temperature, right? We need to go for the extrinsic semiconductors. We need to add some impurities to these semiconductors, right? to these pure semiconductors in order to increase their conductivity, right? So these type of semiconductors, right, P type and N type semiconductors are used with different combination, right, to create different semiconductor devices, right, for the different applications in semiconductor or electronic industry, right. So in the next lecture, we'll be discussing all these electronic devices, how these electronic devices are actually created, right, and what are the applications and what are the implications or consequences of these semiconductor devices, or how actually uh, they ease our daily needs, right? So that will be done in the next lecture, right? So that's it for today. We'll meet in the next class. Take